Okay, you might as well begin. And before I jump into it, I want to apologize for not streaming or recording or dropping any new videos lately. I've been sick, bad sinus infection. You can probably still hear it in my voice. I also want to mention I've picked up a new microphone, which seems to be a lot more sensitive. It's going to pick up a lot more noise and ambient sounds around me. So I will do my best to get those cut out. I've got a couple filters running that should keep some of them down. So I could only hope. Again, I'm relatively new to this space and just learning and working from there. So if I go quiet, basically if I mute myself, is because I have to sneeze or deal with the aftermath of the sinus infection, and we'll go from there. Hopefully I'm not too loud. I'm really learning to work with this new mic, and it might clip out a couple of times. I apologize for that. It'll eventually get dialed in. It'll just take some experimenting and some time and some constructive feedback if you feel like posting anything. So I want to thank you for joining, checking out the stream. If you like what I'm doing, definitely like and subscribe. Follow me. You follow us on Bluesky. I don't know how often I'm going to post. I should have a link on the YouTube, maybe in my Twitch information. If not, I'll get it there shortly. Social media is relatively new to me. I never really played much around with it. Never really saw a need, but community engagement is where a lot of it is. So I'm working on it. Just be patient. So last time we were working on wiring in the stepper driver. This is the last major system to incorporate in. Then after that, we'll have just the auxiliary stuff like the fan, the active cooling to wire in, to plumb in. A few small details we got to kind of finish out, like add fiducials that we can add to the PCB. And then hopefully within one more video or so of cleanup, we can start the PCB layout. Hopefully we can get to that soon. We'll see where we end up after here. We only have a few more components to wire in, a couple of resistors, a capacitor, and then we got to plug in all our control signals from the ESP32. And then just finish all this wiring and move from there. I haven't rearranged the symbol yet. I'll see how it goes. I might end up rearranging it later. It depends, because the way things are going to be tied together. But we'll go. We'll see what we need. So again, I'm referencing the data sheet on my secondary monitor just to make sure I have all the values. So we're going to need to grab a capacitor. All right. So let me get over here. I already kind of pulled up the information for the connector we're going to use for the fan. It's a JST. I've used it before in other projects, and I've got a little kit with the crimpers and terminals and everything to kind of put the assembly, the harnesses together, and it works really well. There's no reason to do anything different and go with anything different. The one key to developing products to put on the market is try to stay as modular and consistent as possible. Try to stick within, if you have complete control of the design, just try to stick within as many consistencies as you can. For one thing, that'll be better stock control, inventory control. You'll have a better grip and handle on what you have in stock, what you need to order. Less chance of mixing parts together. That kind of thing. It makes your whole life easier. Some parts you can't help because the limitations of the design, the component, whatever. You may have a requirement that nothing else will solve, or nothing that you already use. So don't stick to that rule if it doesn't make any sense. But things like connectors, try to stick within like the same series, like same sky or Phoenix or whoever you like, whoever you prefer, for whatever reason, if you can stick within that, it's going to make your life easier. And you'll get to see more of a glimpse of that as we move forward. So 603. So the first capacitor we need is a 470 nanofarad, 0.47 microfarad. 0.47. Try to get that 50 volts, X7R. No, we just kind of like look for stock and cost. Taiyo Yuden, that's a pretty good price, 17 cents. Stock is acceptable. It's not always about cost, but Taiyo Yuden, yeah, 329,000 at 15 cents. That's a pretty good, comforting number. Yeah, we'll just go with the Taiyo Yuden. If I'm pronouncing the name right, I'm sorry if I'm not. 329,000, 10% tolerance. Yeah, that's fine. Meets all their specs, and it's a good. I've used this brand before. Again, if I'm mispronouncing it, I apologize. I'm not trying to be disrespectful or anything. So it's just the way it goes. So it's an 0603. Let's just copy an existing symbol. We're going to rename it. All right. So we know it's an X7R. All right. 0603. So it is a 474, 470 nanofarads. I think it was 50 volts. Let's double check. 50 volts. AAA. Let's make sure that is within our capacitor tolerance. AAA is 10%. 10%. All right. Perfect. Copy that. Okay. Just save it before we go into it. And properties. Footprint stays the same. 47 microfarad, 60 volts. Let's verify the temperature range in the RoHS. I think the temperature range will be the same. 55, it's RoHS. Is it Q200? No, it's not. It's perfect. Leave that alone. Only because I don't want to. Yeah. I don't want to mess up the spelling. Like butchering companies' names. Taiyo Yuden. Manufacturer's part number. Again, everything that I'm doing will fall in line and make more sense when we go to build up the bombs, the bill of materials and everything. It'll all fall in line. 15 cents and 035. That right? 54. Okay. Now, anybody who's been following this series knows we've got to throw it into our ERP solution, Odo. What was it? Oh my goodness. I forget SUI is like 15 cents. Category capacitors. Let's get the description as in here. Reference. Oh, all right. Purchase from Mausa. And we'll save that. Good. Here, we'll save that. Control S. Save that there. Go to our schematic. Get that closed. And go ahead get that little fella placed in here. Okay, so now we need 2 more parts to set up the basically it's a voltage divider for the voltage reference. So basically, the typical diagram pulls off of this guy. And pull you up a little bit. Get you out of the way. Has that coming off. And then there's going to be a voltage divider to set a reference to AV ref and BV ref. This is a little bit messier. I could have moved those pins over, but it's fine. Schematically, it won't be as pretty, but it'll work. So I need a 50K ohm resistor. Let's drag this up here to make it a little bit easier. Hello, come on. Passive resistor. I am just upsetting my computer all day, all left and right, man. Every which way but loose. Okay. It's just a voltage reference. We're not really looking at current. So we need a 50K. All right. We're going to go inch 0603. Oh. That is tight tolerance right there. That is like, I bet you that thing close to military grade. Not really looking for it. 50K. 603. So now here we go. 14 cents, 10,000 in stock. That actually isn't too terribly bad. It's an odd value for an 0603. It really is. So we're going to go ahead and go with the Yagio, 14 cents. Oh boy, it helps if I stop hitting the wrong buttons. Me and my old age. And here we've got some coming in, 20,000 more coming in January 6th of next year. And we're already near the end of November. 50K. I think I've already got some of these on hand if I absolutely need to use them for the other build I made. But I doubt I should be able to get these again. Just to show you, we go to DigiKey. If we have to, we can source alternative. They've got 45,000. Newark Electronics, if we have to. It's 2,600 in stock, and the pricing's all going to be around the same, give or take a couple of pennies. It's always good to be prepared to find multiple sources for products. I just find it's easier to try to get as much from the same source as possible. It just limits how many shipping charges, how many things you're waiting on. That's why I stick to Mauser as much as possible. I like DigiKey. I have nothing against DigiKey or Newark. Mauser's my go-to. I've been going to them for years. Small orders, but hey, they sell in small quantities. When you get into the larger companies, they specialize and only want to sell you in MOQ of full reels. Minimum order quantity. So yeah, but you get really good price breaks from those more specialized vendors. But enough of that. Let's get in here. It's an 0603, so let's copy this symbol and rename it. So it is a 50K. 603. What's your voltage? Say 75 volts. And resistors, AAAs. 100 milliwatts. All right. Copy that. Promise you, we're getting in the end of adding parts. 50K, 70 volts, 0.1%. Okay, is it 55, 155? It's not automotive. Get that out of here. It's Yagio. Oops, come on. Get you in there. $0.14 and 0.52. That is 50K. Right. Save that. More of the same. Where's CO603? 50K. All right. And then the next one is a 30K. Back to search results. Get rid of that. 30K. All right, and more of the same. Panasonic's good stock, good price, and we'll probably go that route. TE, yeah, let's go with the Panasonic. Let's go here. Duplicate. Rename. Okay, so it's 30K. Their voltage. 75, and it is a Q2. Is it the same power? All right. Okay. $17 and 0.48. Things become muscle memory after a while. Mm-hmm. Okay. 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 So, yeah, it's not the prettiest. All right, so there we go. We plumbed in the majority of our stepper control driver. Let's kind of slide this guy a little bit over. There we go. Pulling this guy in. All right. Now what we have to do is plumb in our controls. These symbols, N means not, which also means it's inverted or active low. It just tells you what you have to set the logic level for this to be active or not. So to have this chip actually enabled, this actually has to be pulled low. To reset it, you pull it low. To sleep it, you pull it low. To basically reset and re-index everything, reset the index, I think, or to rapidly adjust to, I'd have to read the data sheet, but the home, but the direction, the step input, which is basically each pulse indicates an actual step. So all that has to be calculated out in the firmware. But that's something we'll come to later. Mode 1, mode 2, those are all, well, these two are either high or low depending on what we're going to select. So let's get all this stuff plumbed in. ESP32. Mainly because STP, copy that, step direction. Yes, I can. So that would be under the DIR. That is now an input. That'll make life a little bit easier. So I wonder if I can copy all those, come to the separate driver. Because if this works, this will save a lot of... Yes! It saves a lot of time. I know it's crazy, but yes, that will save a lot of time. That I don't have to go back and forth. I can just copy all those ports, bring them over here, and plumb them in where they need to go. Change this basically to make it make sense. So reset. Hello. Stop being so... But now the fault is different. So we may have to actually wire that in. I'm gonna have to pull up the data sheet. Let me just copy that. cancel. Make sure we wire that in properly. All right, so it'll give us how you wire that fault in. I think we just have to pull it up, and we'll be looking for like a low, if I'm not mistaken. Fault. It'll show it on here. It'll show how you use the fault. And fault. Here we go. And fault. Yep. So you pull it up with a 10K. And it'll tell us things we should be pulling up. We'll get all that solved. Okay. So yeah, so we'll need a couple 10K resistors, which is good because I think we've already got them added. So that's fine. Like I said, datasheet's your friend. So what we're going to do is step fault. That is technically an output. Let's grab a 10K ohm resistor. Now, 2.3 out. So we can still use. So we can use their 3.3 volt out. We just tie it into our standard logic 3.3 out. Technically, they say voltage potential. It won't cause a problem. All right, let's get you plumbed into you. There. All right. All right, so now the data sheet says we should pull N home up to 3.3 because it's a not input. Now, sometimes some of them you don't have to worry about. So let's see here. N home. There we go. N reset. Okay, when driven active low. So what we can do is we can set a default mode when the unit is powered up so nothing moves that shouldn't move. Do our best to do that. So we'll clean this up. We'll add some control logic just to help make sure that nothing gets too crazy. So it does recommend to pull up that, but I don't think that'll cause a problem because I think it already has an internal pull up. The home, the let's get this stuff plumbed in first, and we'll figure it. No, stop. Step mode. It's an input. Input. Now the decay we can leave floating. That won't cause a problem. So let's set down decay. we're going to do, kind of give ourselves a little bit more room, because I'm going to throw net labels on here. We're getting a little crowded. Step enable. All right. So we're going to let's make sure our logic is sound. So enable and reset. Needs to be a logic. Oh, okay. All right. Okay. So the end home. Okay. So that's an output that you can indicate to a microcontroller that it's at basically at the home state of the step table, basically index position 0. Yeah. That's why. So home can actually be unconnected because we're not using it. It's been a little while since I had to actually design around this. I had to double check. Let's double check and sleep. Let's see, high to enable device. Logic low to enter low power sleep. Internal pull down. So I'm going to need to... Actually, I could tie that. We can tie that to... No, we can do that. We can just pull that up. It looks like we can just tie that to 3.3 volts. Let's just go ahead and do that. Let's just pull you to 3.3. The reason this has a pull up resistor is because it's a an open collector transistor setup, so you'll get low pulses when a low when you've got a fault of any type on the device. So step correction. So what we're going to do is we're going to throw in 2 more 10K resistors. So if that is active low, logic high to disable device outputs. So what we're going to do is we're going to want to pull those high. Okay. I should have that guy. So what this should do should give us a little bit better control when the device boots up, and it doesn't want to, like, hopefully at the end of the day it doesn't cause the stepper motor to like skip or anything while the device powers up, while the ESP32 boots up. This will give it like some default control. STP enable here. I don't know why I keep doing that when I can do it. STP reset. All right. So that should give us a little bit, like I said, of control for where it's not going to want to do something while everything powers up, while everything energizes. That just forces, that hopefully will force a state. We may have to, depending on testing, decrease the resistance, give it a little bit of a stronger pull up, but we'll see. That way the microcontroller then can pull it low. All right. Okay, so now the only thing to really add in here is the connector. I'm just going to go and throw it on here. I'm not going to make another schematic sheet just for one connector. It's just not worth it. So again, this is one I've used. I'm just going to go ahead and get the footprint and the model and everything. It's a right angle, which is fine. what we can do here. All right. All right, so it looks like I have everything. KiCad. All right. All right. Now we need connectors. Actually, let's get the footprint in. Yeah, being sick really still messes with me. Import footprint. Downloads. KiCad. Get that guy in there. Move you out of the way. Put you here. CN. I just like that better. We'll keep it named as the footprint for that part because I don't think anything else will really fit on it, or not that I've seen. There might be an off-brand that would work, but I don't want to take the chances. I would rather just have to duplicate. All right. View it, of course. All right. Okay, let's see which way you want to go. All right. Pop, 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 pop. Make sure. Oh, all right. I have to offset you and rotate you some more. Pop, pop, pop. You're still stuck in there. Pop, pop. Yay. Rotate. Nope. All right. Pop, pop, pop. There we go. Not going to be perfect. Actually, that looks pretty darn good. Okay, we're going to save that. Now, let's go to components. With a 4. You know what I do right there? Just going to duplicate that little guy. And rename it. All right. So, let's see how they describe this. It's just a header. They consider it a header, so that's what we're going to do it to. KH. And let's just grab this. Copy the whole thing, save. Annoying, I know, but CN connector. Let's get that cleaned up. Connectors. That's that fella right there. Looks like I'm gonna have some pluggable through a hole. What's our, let's see, right angle. No, you're not through a hole, you're an SMT or an SMD, surface mount device. What's your pitch? Of course you don't say there. Just go grab it out of the data sheet. What's your pitch? Hello. Hello. I'm probably overlooking it because I'm tired. Oh, yeah. Two millimeter. Well, wait, that's for a through hole. Let's make sure the SMT version is the same. Yeah, 2 millimeter pitch. All right. All right. May not be 100. See, voltage and current rating. We don't need that guy anymore. Yeah, we do. All right. Let's see if we can find that in here. No, we can't. That is not fun. Oh, here we go. 100 volts, 2 amps. 2 amp. 2 amp. Does it give our temperature range? 25 to 85. Yeah, 25. All right. All right, there's that. So Molex is JST. Manufacturer part number. Probably would have been easier to copy to make a new one, but I have this framework. Mauser part number 079. What's our large quantity? Raw button as usual. 1000. Oh, 369. 69. And now the mate. We're gonna have to add another because it's not just a mate, because we also need terminals. Show name. So the mate, which is the physical component that's going to plug into this guy. So I've already sussed these guys out. So this is the actual housing. This is going to be a 4-circuit housing. So basically, it's this part that plugs into it. It's going to be 4-circuit. All right. We're just going to copy that. That's in for the mate. And then the terminals are crimp terminals. And there are the parts there. That way we have them consistent with on the schematic. Those just make our lives a little bit easier. I think it was 79 cents. Yeah, for one. Category connectors. The reference in here. Okay, yeah, okay, that looks all right. Reference, purchase, Mauser. Oh, wrong one. All right, bam, bam, saved. Okay. Back to this guy. Okay. Save it 4 pins. They'll match properly. All this stuff doesn't really matter. All right, so let's go over to our schematic. We're going to throw that guy right in here. This is just going to be for the fan. All right. So here's where we'll get to decide on how we want this to be. So let's save this. Let's go over to the ESP32. All right. And Fantac and PWM. Grab those two, copy those, paste those here. All right. What I'd like to do, make sure. Yeah, so our fan is 5 volts. And I'm jumping all over the place, not paying attention to what I'm doing. Grab that. Power supplies. 5 volts. All right. And TAC and PWM. So TAC is an output from this connector, and PWM is an input from the controller, ESP32. All right, so we're gonna plumb you guys together here. Plumb you in there. All right, okay. Well, let's kind of pull you guys down a little bit closer to this guy. Stop. All right, here we go. All right. So we got the stepper motor all, the stepper controller all plumbed in. So one of the things we want to throw in now are fiducials, and we'll throw those on the root page. So in things like this, in the schematics like this, a lot of times in the root or cover sheet, as this is called, sometimes this is where you'll throw, not only your hierarchy connections, you could do all kinds of connecting, tying these guys together, throwing ports and lines to tie all these together. I typically don't like doing it this way because it becomes a nightmare. Personally, I just, use this as basically just like helps with the sheet order. Your first sheet would be that ESP32. But also we'll put like mechanicals, like fiducials, mounting holes. We're not going to throw mounting holes in this guy. Although maybe we should, but I'm not going to right now. Testing and feedback, because there might at least, testing might actually be one more iteration. We might want mounting holes. That might be an oversight on my part. But we'll see how things go once we start doing the PCB layout. It's not like we can't add mounting holes later and set them up to actually represent like the screws we will want to use in the design and things like, at the end of the day. But we do need to create some fiducials. All right, so they're going to be considered components. There's no really easy place to do it. So we're going to actually create a new footprint. We're going to change that reference to FID or fiducial. Let's get these guys out of the way. It makes it easier to draw what we're trying to do here. Get these guys out of the way. So a fiducial is typically just an SMT pad. Let's see here, add pad. All right, so it's going to be typically a circular. The diameter is a 1 millimeter. All right. Okay, technical errors. There's no paste. Now, we're going to want to do our own masking for it. What this would do is this would, well, let's see here. I think this would create a default mask for it. Or, oh, okay. So no, let's go to here, mask, clearance overrides. Slaughter mask 1.5. So you want a 1 millimeter pad. Let's make sure all that's right. Sure. 1 millimeter, but with 1.5 millimeter clearance around it in diameter. Now, if that is, that might be radial, so, or radius versus diameter. So let's see what, yeah, 0.75. So since it's radius from the center, we don't need it that big. So that'll create the solder mask They'll open it up. Basically, you just see the bare board around the fiducial. Basically, so the SMT pick and place machines register it properly. They can be quite picky. Technically, we don't need a silk screen, but an overlay. We're gonna save this. You know what? Let us change the name. We're gonna call it FID 1.0 by 1.5 millimeter round. All right, that's the name of the footprint. Save that. Now, for the sake of simplicity, let's just open that. We're going to create a new symbol. Symbol name. Fed 1.0 by 1.5 millimeter round. We're not gonna number of units per package. Not worried about that. Not worried about that. We can exclude it from bill of materials, which is kind of cool. You can do this because you don't need a fiducial on a bomb. It's not something you buy. We don't need to show this. All right. All right. So all we need to do, move you out of the way. Let me draw a circle. Hooray. And then pin name 1 and 1. It's not going to be visible. Well, we're going to make it visible for now so we can move it. Don't care about that. Electrical type unconnected, so it doesn't matter. We're just going to kind of throw it in there. And we're not even going to see it. There we go. This way you don't break any rules and the pad and everything shows up. I don't want to cause any issues with KiCad, but we're going to throw that in there. So right off the bat, we're going to assume now typically, so fiducials, there's typically three types. You have basically what they call global fiducial, which will be on the rails of like a panelized board. So imagine your PCB is in like a grid array of like say 4 across by 4 up. So 4 times 4. Yeah, that many boards arranged in a grid array. So typically also with most pick and place machines, you have what's called a rail at the top and bottom of that array, and that is so it can feed through the equipment. So basically the conveyor system can actually grab hold of it, convey it along, clamp down onto it for the different operations. So a global fiducials will be on the rails. So the entire board will be covered by those fiducials. The machine would register those and calculate all the pick and place locations based completely off of those fiducials once it knows the matrix array. Then there's board level. So there'll be each PCB will have their own fiducials. Typically, you want to have a minimum of 3 to get your offsets, all your calculations for X, Y coordinates, as well as like twist, because boards can be kind of skewed in a pick and place machine, so they can be kind of slightly rotated along the Z axis, and that can throw this way the system can actually calculate and offset everything with at least 3 fiducials. And then you have local or component level fiducials. So something like a very fine pitched microcontroller, you can actually have fiducials assigned to it, and that can help the machine register its position and calculate it so it places it perfectly. Typically, I don't really worry about that. I haven't really seen too many cases where a local has really been too much of a benefit, especially with the newer machines, but you never know. So we're going to assume we're going to have top and bottom. So we're going to go and just throw 6 fiducials in here right off the top of the bat. We can delete them, update the board. Who cares? It's not going to hurt anything. This way they'll already be over there. Let's see if we can throw No, I need a text box. It's right on a rectangle. So this is what I like to do. Okay, so we're gonna throw text in there. All right. Let's capitalize it. Do Schultz. All right. We might go through and annotate the rest of the schematics with boxes and text like this. Who knows? Some people like them. Some people don't. Sometimes I like doing it just because. So then what will happen is these guys will get translated over as just basically pads that don't electrically connect to anything. And you place them on the board, and that way you can get your XY placement as well as your Z rotational offsets. That way when the machine calculates the actual placement of the components, it'll be able to do it. Okay. So let's go back to here. I should have opened this before, but I didn't because I don't like to be prepared. All right. So, mouse is getting a little plugged up here. I'm just having all kinds of fun, aren't we? It's cold and stuff, and my internal filter's not working 100%, so I apologize if I said anything or you heard anything under my breath. It's just, it's cold, it's miserable, and my filter's not working 100%. So we've plumbed up our power supplies. So we're going to kind of go through it. So here are our power supplies. 3.3 volt and 5 volt. Yeah, I know it's a waste of components for 5 volts for just one component, but who knows down the road, we might find other uses for it because we do have up to 2 amps worth of power we can drive. Could be for relays. It could be for other external connections. Right now, it's just going to be for the fan. Seems like a waste. I get it, but you know, it's just the way it is. ESP32. That's all plumbed in. We have our boot mode pull up right here. Our ESP enable pull up and the RC timer network to delay its enable. The capacitors for filtering. RS45 interface. TVS diodes, our test points, our jumper for termination resistors. All that looks good. Our basically limit switch inputs or other control inputs, because technically you can program that. You'll be able to program the ESP32 any way you want. I'll do my best to have the best possible example code with it. I can't promise anything. I'm not much of a coder. I'm learning. I'm doing my best. But so here's for the limit switches, the control inputs. Basically the same circuit. 3 control inputs could be used for additional limit switches. The USB UART, this is used for programming the device. Basically mimicked ESPs, expressives, schematic and component choices. So we got TVS diodes. We've got test points galore. Our auto programming circuit right here. All right, okay. And the big important guy, the stepper driver. So now I do see something I want to kind of touch up real quick while we're here. I want to kind of be consistent where it displays the capacitance, the voltage on that component, on that capacitor. So let's get up here. We know it's this guy. Properties. 100 microfarad. It's okay. We don't need to show that, but we'll show you this. Okay, we will save it. Then come over to this symbol, and I think we can do update. Update, reset, update. All right, which is kind of weird because when you update visibilities, oh, so if I edit this field, oh, it's unvisible, which is fine. I mean, I'm not going to cry about it. It worked. Let's get rid of show field name. We don't need that. I don't know why I did that. I'm a goober. I'm an idiot. All right. Since there's no actual package, we don't need to put that, but we have our capacitance value and our voltage rating for that capacitor. All right. All right, so we have our stepper driver all set up, our logic controls. So when we apply power at first, power up. We could do some other things to control this if we really, really absolutely wanted to. We could put even a relay or something in here that stays off, that we can turn the power on directly to this guy. We'll do some testing. Who knows? We may have to do something like that. Not 100% sure, but we will figure it out. We will figure it out together. So this pretty much concludes the actual schematic capture. Next, we will be going on to PCB layout, and that'll be the next video I actually get done. We will start that and move along that process. That will take some time. Some things you want to make sure you lay out properly, like power supplies. We'll want to take our time laying this guy out. Pretty much everything possible, figure out our logical placements on the board, figure out our size and everything else, and go from there. But for now, I think we're looking good. We'll finally be getting into PCB layout, and I think that'll make a lot of people happy. Well, thank you for catching. Again, sorry for having this, sounding weird with this cold, this infection I was fighting. But apologize for anything I might have said under my breath. Just fighting this, and my brain filter is just not working properly. Been frustrated and feeling like junk. So I will catch you guys in the next video, and thank you very much.